Section 12.6, Triple Integrals and Cylindrical Coordinates, Video 5. This example, which is the final example in the book, but I think I'm going to do one more after this, is example 4 on page 733. And the directions are straightforward. Evaluate this triple integral. It's already set up for you. We're going to integrate x squared plus y squared, dz dy dx, and here's the limits of integration. Now, could you attack this straightforward? You could try, but I can tell you right now you're going to run into problems. Go ahead, I dare you. Pause the video. Try to integrate this rectangularly. Sure, the integration with respect to z is easy. Stick a z on here, substitute 2, and substitute this. But when it comes to integrating the y, you're going to get stuck with something that's impossible to do rectangularly. If you don't believe me, pause it and try it. When you've reached the point of no return, resume the video. But this isn't an uncommon phenomena in applied calculus, namely physics and engineering, where you set up an integral for whatever reason, and when you set it up and try to attack it, you realize it's either difficult or impossible as is, and it usually is contingent on the coordinate system that you're using. This one clearly is set up in rectangular coordinates because of x, y, and z, but there are elements about it that suggest to do cylindrical coordinates, namely the presence of this guy. Any time you're doing a double or triple integral and you see square root of x squared plus y squared, that is just screaming, change me to polar coordinates if it's a double integral, or cylindrical coordinates if it's a triple integral, because this expression collapses down to a single letter, and it's this expression that mucks things up, where you get to a point where you can't integrate it rectangularly. So we're going to do this in cylindrical coordinates, but in order to do that, you can't just go in and change all the x's to r cosine thetas, all the y's to r sine thetas, and drop in an r, because you need to know what this solid looks like and the equations that define it in polar coordinates. These equations define it in rectangular coordinates. For example, this is y equals the square root of 4 minus x squared. I know it's y because it's the second differential. So what does the equation y equals the square root of 4 minus x squared look like in polar coordinates? Well, you can't just straight up make the changes. You have to set up the solid, redefine it in terms of cylindrical and polar equations, and then reset the integral, and then take it from there. All right, so we're going to start by trying to sketch the solid. So we'll say sketch the solid E. And in order to do that, we need to know what the limits of integration are telling us. The limits of integration are telling us that the x is between -2 and 2, because the last integral that we'll evaluate is dx. The middle integral is telling us that y is between negative square root of 4 minus x squared and positive square root of 4 minus x squared. And the innermost integral, the dz integral, is telling us that the z is between the square root of x squared plus y squared and 2. You should start with a more complicated one, namely the innermost integral, because it's going to have the most variables in play. So let's start with, what does this look like, or what are these equations? So we know that this is bounded on the bottom by z equals the square root of x squared plus y squared, whatever that looks like, and on the top by z equals 2. I know what that looks like. That's a plane. But what does the bottom of it look like? Wait a minute. Go ahead and start thinking cylindrical coordinates. This, in cylindrical coordinates, is r. And when we talked about special types of graphs in the second video, one of them was z equals a constant times r. In this case, z equals r. This was a cone. Now be careful. Previously, I said a cone is both the top and the bottom, but because this is z equals the square root of x squared plus y squared, and by definition square roots come out positive, This is only the top half of the cone because this is positive z values. So when I start sketching the solid, this represents z equals r. If you think of this as y equals mx plus b, the slope is 1. So just draw a line of slope 1 in the xy plane, and -1 also because it rotates over there. And voila, there's your cone. So there's z equals the square root of x squared plus y squared, or z equals r. Since we're going to cylindrical coordinates, we might as well go ahead and start calling it z equals r. Now the top of this surface is bounded by z equals 2. So we just need to go find 2, I guess there's a convenient place, and say that the top is z equals 2. Okay, we already know that we're going to have to project this down to the xy plane, but let's talk about what our bounds say in the xy plane, just to make sure everything is consistent. The bounds in the xy plane will give us the region over which we evaluate the double integral, in other words, the region D. So the equations on the bottom and the top are very similar, except one has a negative. Y equals the square root of 4 minus x squared, and the bottom is y equals negative square root of 4 minus x squared. What do those graphs look like? Well, the answer is they're both semicircles. The top one is the top half of the circle, the bottom one is the bottom half. How do you know they're both semicircles? Well, square both sides and move the x squared over. If I square both sides, this becomes y squared. Move the x squared over, we get x squared plus y squared equals 4, which is a whole circle, but this is just the top half of it because the square root is positive. The same thing happens down here. If we square and move the x squared, we get x squared plus y squared equals 4. But it's the bottom half because of the negative, meaning that the y's here are negative. So it's the top and bottom half of the circle. What's the radius of the circle? 2. So here's y equals the square root of 4 minus x squared on the top, y equals negative square root of 4 minus x squared on the bottom, and the x's are ranging from -2 to 2, which is what we had over here. So everything is suggesting that that's the solid, and this is its projection into the xy plane, the region over which we'll evaluate the double integral. I think I'm going to pause this video and start another one, and in the next video we will take this picture and use it to transform the triple integral in rectangular coordinates into a triple integral in polar coordinates.